Yeah, dear students, today I am going to show the demonstration of another experiment, namely photodiode characteristics. You have already done so many experiments on diodes. You have already drawn the IV characteristics of PN junction diode, IV characteristics of GNR diode, and you also studied light emitting diode characteristics. The diodes are operated either in forward bias or reverse bias. Zener diode especially is operated in reverse bias under breakdown to use it as a voltage regulator. LED is also a P-injection diode, may be heavily doped, made by large bandgap semiconductors, and it emits light in the forward bias condition. That also you have done it. The emission of the light wavelength by a LED depends on the material you choose, that is the semiconductor material, and it depends on the band gap of the semiconductor. If the band gap is low and less than 1.2 electron volts or 1.4 electron volts, then it cannot give light in visible spectrum. In general, the diodes like ordinary injection diode, GNR diode, they emit the energy in the form of heat across their junctions, but not in the form of light. But LED gives the energy in the form of light. And now we will see another diode called photodiode. Photodiode is also a p-n junction diode made by semiconductors but operated in reverse bias. Photodiode is also called as photodetector or photosensor, and these are used for sensing requirements. In optical fiber, we use LED as a source and photodetector, that is photodiode, as a receiver end. So basically a photodiode converts instant light into the electric current or voltage. So it is a reverse phenomenon of LED. LED takes the applied voltage as input and it gives the light output. In case of photodiode, it takes light as input and converts that input optical energy into electrical energy. And these photodiodes can be operated in two different modes as photoconductive mode and photovoltaic mode. In photovoltaic mode is also called as zero bias mode, where we don't apply any bias but incident light makes the current to pass through the circuit. And for example, the photovoltaic mode operation of a diode is a solar cell. This is also there in our experiment. We will see shortly the solar cell experiment also. In photoconductive mode, which is a photodiode now, we apply some reverse bias and make the charge carriers to move away from the junction and pass through the circuit and give some current. So a photodiode is now we are using is operated in photoconductive mode. But these photodiodes are different types like photo PN junction photodiode, we have avalanche photodiode, PIN photodiode. PIN means P type, intrinsic, and N type. Three reasons are there. And in say a photodiode, the reverse bias helps to pass the current in the circuit. Whereas in avalanche multiplication, the process is applying very high reverse voltage and thereby the current passes in the circuit. But whatever may be the diode type we are taking, all of this more or less basically works on the same principle. So that is the creation of electron hole pairs. LED functions on recombination of electron hole pairs. They recombine. Here, in this case, in photodiodes, we will have the generation of charge carriers, electrons and holes. These generated charge carriers are separated out by applied reverse bias, which is called as photoconductive mode. So, in this experiment, we will look at the characteristics of a photodiode. Yeah, students, this is a photodiode. See, this is in black color. Only the light that is falling in it can be passed through it, and that will be converted into this. This is a wow. You can see it. This is a photodiode, and I will show you the board here, the experimental kit for a photodiode characteristics. You can see the circuit diagram. We have two analog meters. This is to measure the voltage and this is to measure the current in the circuit, milliammeter. And here if you come down, there is a symbol for the photodiode which was connected inside the board. That's why you are not able to see it. Here you have to connect ammeter between these two terminals. Okay, and between these two terminals we connect a voltmeter to measure the voltage across the diode. This is across the diode, and this is the input voltage we will give from the supply, and you can change this by to vary the voltage from 0 to 30 volts. And here we have a socket, and this socket is used to attach the light source so that the light will fall in the on the photodiode. Now, as I said here, the photodiode has to be connected, and inside that is now taken out, and this is the photodiode module. Inside this we have the photodiode, and we'll make the light to fall on the photodiode. So this is the light source which I'll make to fall exactly at the same height on the photodiode which is there in this enclosure. And the output from the two leads will be connected to this, and this I will add these two output leads to the circuit diagram or circuit where we have a photodiode. We have to connect it. And also see that this light is now, okay, this is a light source, it's a bulb, and we are connecting this bulb to the board, and through which, using this knob, I can change the intensity of the light. Now I'll explain how to connect the circuit. Before that, you can see here that you have used different diodes. So this is the symbol for ordinary PN junction diode. This is and this is N side and this is P side. You also did GNR diode, and this GNR diode is having a Z1, so we have a GNR diode like this, and this is GNR. And we have another diode called varactor diode. This is a symbol for varactor diode. We have another diode called Isaki diode or tunnel diode. This is the symbol for tunnel diode. Okay, and now you have already done the light emitting diode. As the light is emitting, the arrow marks is outside. This is LED. So this is PN diode. This is GNR diode. This is varactor diode. And this is tunnel diode. This is LED through which light is coming out. If I draw another diode, and if you are making light to come on this, if light falls, this is photodiode. You can also have phototransistor. Basically, the photodiode works on the principle of a generation of electron hole pairs and converting the incident light energy into electrical energy. And come to this board. You see it how I am connecting here. The connections are quite simple. See here they have marked to connect an ammeter. I am taking the ammeter here. The two are there here. And take one of the lead, that is positive lead, connect to the positive terminal of the meter, and take another wire, connect negative terminal to the negative side of the ammeter. And I'll take here the voltmeter. I'm connecting the voltmeter from here to here. And then the second point of the voltmeter 1 is connected to negative terminal of the voltmeter. Then we need to add the input supply. So I am taking another wire, I am connecting negative terminal to the negative terminal of the battery, and positive end, okay, positive end I am taking here and connecting to positive of the supply. But you should know that the photodiode is operated in reverse bias. Therefore, negative, see this is the negative connected here, and this negative has gone positive of the diode. Therefore, diode is in reverse bias. Now I need to connect here the photodiode. So photodiode box is this. You can see the box, okay, and this leads are coming out from here. So these are the leads of the photodiode I am taking. From this I am connecting these two leads to here, that is positive terminal of the diode here. Okay. So I am connecting this here. This is positive red and this is negative is this. I have connected this terminal. This is the where I am keeping the setup of photodiode, and this is the light. Now I switch on the power. I have already given the power, okay, this, but now I switch on the power from the source. This is the power I am switching on it. And come here, if you see it, I am switched on the power here. This power is coming here, and see light is also glowing. And this incident light is now made to fall on the photodiode. This is the photodiode. If I keep this very close to the lamp, then the intensity of the light that is falling is high, thereby the current produced is high. If I keep it far away here, where the distance is increased, the light that is falling on it decreases, and therefore the output current is less. Therefore we will do how the current in the circuit changes depending on the incident light. So I can keep it here or I can keep it here. Instead of changing the distance between the lamp and the photodiode, I can also alter this. This is the knob, which is just like, so I can make the intensity less. This is the less intensity I can make by turning this. Okay, so almost zero. This is just like your fan regulator. In the house you use fan regulators, and you can keep in 1 number, 2 number or 4 number to increase the fastness. But here it is a potentiometer where I am changing the potentiometer, thereby the current changes and the intensity of the light emission also increases. So you can do this experiment either by using this control to change the intensity of the light in, okay, or you can keep this intensity constant. You can move this either close to the source or away from the source. But in this demonstration, I am keeping the source constant, and I will only change the intensity of the lamp. So when I look at, you have seen that ordinary junction diodes and Zener diodes are made by silicon and germanium. LED is made by large bandgap semiconductors like GaAs. And we also informed you that silicon and germanium are not useful for making optoelectronic devices like LEDs, etc. But photodiodes require good conversion of incident light into electron hole pairs. Therefore, silicon and germanium are the best materials for making photodiodes. Silicon diodes are very extensively used photodetectors in many applications. In addition to this, you can use other materials like indium gallium arsenide. So silicon, germanium, indium gallium arsenide are the materials generally used for making photodiodes. Now students, look at this experiment setup. We have made the connections and we have added the meters here. This is the voltmeter and this is the ammeter. And we connected the photodiode at these 2 points and 2 ends, and you look at this. This is now fixed and you can see the photodiode here, the photodiode setup. I have fixed this intensity. At fixed intensity, how much current that is flowing through the circuit by varying the voltage, we will see it. Okay, now I am taking 0 voltage and current is also 0. Yeah, now look at the tabular form, serial number, voltage I will change, and I find out the current for various intensities. So I am taking intensity 1, I will do the experiment, and intensity 2, I do it, intensity 3, I do it, and then I draw a graph. So this is the intensity, fixed intensity, how the current is varying. And this is intensity 2 and how the current is varying. Similarly, intensity 3 and the current value we note it down. First, I have adjusted the voltage initially to 0 and current is also 0. Now, look at this. I have not changing the intensity of the lamp. It is fixed. The distance is also fixed. So, light falling on the photodiode is constant. At that constant intensity, I am doing this experiment. So I am slowly adjusting this value. See this is 0 to 5, 5 to 10. There are 10 divisions in between, and therefore each 2 divisions is 1 volt. So I am slowly increasing this to value of 2 divisions, which means it is 1 volt. And corresponding value of current, if I look at it is 2, see look at around 2.8 because it has not reached the 3. This is also 0 to 2 volts, 10 divisions is there, each division is 0.2. So therefore I am taking the value of current as 2.8. Voltage is 1 volt and current is 2.8 milliamperes. Now I will increase the current to 2 volts, and I'll look at the value of this, and this is around 3. So I note down 3. Now I'm going to 2.5. This is 2.5, and the current value is slightly above this, and therefore I am 3.2. I will increase this to come here, it is 4 volts now. I am slowly increasing this to 4 volts. I find out the current. Current is 3.2 only. So I write 4 volts. The current value is 3.2. Now I am going to 5 volts. It is 5 volts. You can see that, and still I'll adjust it to 5, exactly 5, and I note down the value of current. So current is no much change is there. If I see without any parallax, this is still struck at slightly above 3, so I am writing 3.2. Likewise, if you go on taking the readings, as the voltage we are increasing it, keeping the intensity constant, the current value slightly increases initially, then becomes constant. So I am also increasing the current to suppose say 7.5. I have increased it to 7.5. And see, there is a little increment in the current, that may be 3.4 or so. If I increase to 10 volts, I am increasing this to 10 volts. You can see it is 10 volts now, and I write the corresponding value of the one. This is around 3.6. Almost afterwards also, even if you go it remains constant, because if you draw a graph between the voltage and current. Here the current in the photodetector passing through the circuit is a reverse current. Because we are operating this in reverse bias, the current through the diode is reverse saturation current. And hence you can plot a graph by taking voltage V here and current I in milliamperes. So it may start here and initially goes something constant and increase and then it becomes constant like this. If I increase the intensity for next value, the curve goes like this and becomes like this. If I still increase it, it becomes like this. So you have to write the different values. Suppose say this is intensity 1, intensity 2, intensity 3, where I3, okay, we have I2 and I1. So I1 is less than I2, I2. So higher the intensity of the light falling, the more the current it produces and we have a saturation region. So these are the characteristics of a photodiode. Now I am going to see the next intensity and note down the values. Here I will come it. I will now show that I am keeping this voltage to 0, okay, and current is also showing 0 value, and I go on increasing the intensity of the light, keeping the photodiode at the same place. So I am increasing the intensity of the light, I have increased it. Now I will try to do the experiment. 0 for intensity 2, the current value is 0 only. And I am going for the increase of the voltage by a small value or 2 divisions. I am going for 2 divisions if I say it, okay. This is the 2 divisions, means that it is 1 volt. For 1 volt, see the current is 4 milliamperes. So 1 volt, 4 point something. 4 point, okay, 4.4 I can write. So I'll write 4.4. I now increase this value to 2 point, okay, I'm going to 2. If I increase to 2 I am increasing, and you can see the current is around 2.5, 2.6, sorry, 4.6, and I increase this to 2.5, and this is 2.5, and the current value is 5.2. So here I note the value as, okay, so for 2.5 it is 5, it is showing as 5. Now I increase this to 4, this is 4, I have changed it to 4, slightly increase it to 4, okay. Then I note down the value of current, it is around 5.6, okay, 5.4, 5.4. Now I increase the current to 5 volts, it is 5 volts now, without any, okay, it is, if I go for this, it is 5.8. So I write 5.8. Then I go for 6. This is 6. So the current is 5. Okay, nearly 6. So I am now writing it as the current as 6. Here I have not taken reading, but here I am getting the reading as a 5 point, nearly 5.8 something, same it is showing. Then I go to 7.5, I am going to 7.5, I note down the current value as 6, 7.56. Then I will go to 8, I will go to 8, this is 8, okay, this is 8, I am going to 8, and here we have not taken readings, and it is 6.2, I write 6.2. Then I go to 10. If I go to 10, the current value is 6.6. Okay. For 10, it is 6.6. Then I'll go for 12. If I go for 12, this is 12. The current is 6.8. 6.8. I go for 12.5. 12.5, current is again 6.8. I go for maybe suppose say 15. I am going to 15. Okay, the current is around say 7.4. But you can stop here because almost we have achieved here a linear portion, something like this. Now I will do this experiment for the third intensity. I decrease this one to 0. I am making it to 0. And I change the intensity of the lamp to higher value. I am increasing the intensity. You can see it. This is the intensity. Don't keep very close to it, because if the intensity is very high, then the heat that is received by the diode also increases. There is a chance for diode to spoil. Now for the third intensity, I will start with 0 voltage and 0 current readings. Then I increase to 1 volt. Okay, but see that here, if you see, even as the intensity is higher, the incident light is higher, it can produce and generate more electron hole pairs in the semiconductor, and therefore the current in the circuit is higher even if you apply small reverse bias. Hence, if I just keep it suppose say 1 volt, current is increasing to higher value. So for 1 volt, current is around 5 milliamperes. 5 milliamperes. If I go for suppose say 2, the current is around 6.8. If I increase this to 2.5, okay, it is 2.5, current is almost 9.8. If I still increase this, okay, current has given to reach it to 10. Therefore, even 2.5, okay, and if I go for 3, it is 10 volts. This is for 2.5 volts. This is also 2.5 volts. 10. And after that, you will get continuity. Likewise, you can take a large number of readings for various intensities, and you can plot a graph here, and you'll get a graph. So therefore, here I am doing only 3, but you can do on the VLab simulator 4 to 5 different readings, and you can draw the graph. Thereby we can say that the VI characteristics of a photodiode has been verified, and we are not doing any calculations in this experiment. We are just verifying the VI characteristics of a photodiode. Thank you.